Predicting redox reactions. A redox reaction occurs when one element takes electrons from another element. The element that takes the electrons becomes more negative or has its oxidation number reduced, or it's a reduction, and that is acting as the oxidizing agent. Similarly, the element that's not very good at holding on to electrons loses its electrons, its oxidation number goes up, it gets oxidized by the other element, which is the oxidizing agent. It's the reducing agent as it causes the reduction of the other element. All of that being said, for this reaction to occur spontaneously, we need an element that's good at oxidizing, an element that's good at taking electrons, to be in a high oxidation state, so it's ready to take electrons. And we need an element that's good at getting reduced, or we need an element that's good at reducing another element, or good at giving up its electrons, and it needs to be in a situation where it still has its electrons. So let's look at our chart here and identify a couple interesting elements. Let's look at copper, for example, and let's look at zinc. Why not? So to create a spontaneous reaction between these two things, copper is the better oxidizing agent. Copper's better at stealing electrons than zinc is. So copper needs to be in a high oxidation state, like Cu2+. How could we do that? Well, let's say, for example, in solution, we could have copper chloride. That copper, or that is like in a solution, that is effectively copper ions and chlorine ions floating around. And so what we have here is a copper ion that's in a high oxidation state, ready to take electrons if he can find somebody who's not as good at holding on to his electrons. He's a strong oxidizing agent because he's ready to oxidize the other atom. When he does that, he'll get reduced. Alternatively, for a strong reducing agent, we can have something like zinc. For a strong reducing agent, he needs to be somebody who's not very good at holding onto his electrons and is in the state where it's ready to be oxidized or ready to lose its electrons. So in this case, that means that it's on this side of the table. So we have zinc solid. So now what's ready to happen here is the zinc, which isn't very good at holding onto its electrons, is ready to give them up. And the copper, who's very good at taking electrons, is ready to take them, and we can get a spontaneous reduction oxidation reaction. The trick to tell if that's going to work or not is the guys that are good at taking electrons or the strongest oxidizing agent are up in this corner of the chart. And these are the states that they occupy when they're in a high oxidation state, ready to be reduced. Alternatively, these are our strongest reducing agents. Right down here. And this is what it looks like when they're in a state of low oxidation state, ready to be oxidized. So these guys have electrons and don't hold them well. Right? That's what's going on down here. And these guys don't have electrons. And are ready to take them. And they're strong at doing that. So, This copper, who's strong at taking electrons, is right here. And this aluminum, who's not very good at holding electrons, is here. So he's able to move backwards to this. And this copper, sorry, I meant to do zinc. And this copper is ready to move forward. And so this reduction oxidation reaction can happen. In the simplest sense, we know this reaction as the single displacement reaction, where zinc is taking the place of the copper in the solution. But from a reduction oxidation perspective, we can just write this reaction as Cu2 plus zinc going to zinc 2 plus Cu, where here the zinc spat out 2 electrons, and here the copper absorbed those 2 electrons. So that's what we need to create a reduction on oxidation reaction. We have to have an atom that's ready to take electrons and is strong at taking them, and an atom that's ready to give up electrons and weak at holding theirs. How can we tell that easily? Well, the simple way is to recognize that if we have somebody on the left-hand side, left, that is higher than an atom on the right-hand side, this will work. See, copper is higher than zinc. Lead would also work. Lead is higher than zinc. Alternatively, aluminum would not work. See, aluminum is lower than zinc, so this is a no reaction. So I need the one on the left to be higher than the one on the right. If that's true, then they can exchange electrons in a way that's favorable for both of them. Well, favorable in general, and as a result, the reduction oxidation reaction can happen. I'm going to include a couple examples now where I look at big lists of elements and ions, and we're going to figure out what reduction oxidation reaction would happen by taking the highest one on the left in comparison to the lowest one on the right to come up with the overall reaction.